Hello, welcome to part 2 of Center of Mass. In the last part, we had an example and we showed why this part of this object would be the center of mass. Now I want to give another example, and here we will try to find the center of mass when it's not clear. So this is the one part of the one mass, and here is another mass. This one is 2 kilograms, and this one is 3 kilograms. We want to find the center of mass. Actually, I'm gonna put this 5 kilograms. Now, I'm gonna put an imaginary point here. This would be the center of mass. And we would have here one distance from this mass to the center of mass, and another distance from the second mass to the center of mass. This distance we would call A, and this distance we would call B. Or actually, let's use subscripts. So this would be M1 is equal to 5 kilograms, M2 is equal to 2 kilograms, and this one is X1 for the distance of the first mass, and X2 for distance of the second mass. Now, as we calculated earlier, in order for this to be the true center of mass, the clockwise torque and the anti-clockwise torques should be equal. We have one force of gravity here, which would produce the anti-clockwise torque, and the force of gravity on this object would produce the clockwise torque. This force of gravity on the first object is equal to 20 Newton. The force of gravity on this object is equal to 15 Newton. And the torque on the first object is equal to which is the anti-clockwise torque, is equal to 50 newtons times the distance x1. And the torque on the second object, which will be our clockwise torque, is equal to 20 newtons times the distance from the center of mass. Now, in order for this to be the true center of mass, these two torques must be equal. So we're going to set these equal. 50 newtons times x1 is equal to 20 newtons times x2. This is our first equation, which is very important. If we are able to find x1 and x2, then we will be able to find the center of mass. Okay, so the other equation that we will need here is the distance between these two masses. The distance from here to this object is needed. We have to know how long or how far apart they are. In this example, the distance is 14 meters is equal to d. I forgot to put that in the beginning of this video. So we will add that information to our equation list. x1 plus x2 is equal to 14 meters. x1 is this small distance, x2 is this one, and adding them together will give us 14 meters. So we have our system of equations here, and we have two unknowns in two equations. Using algebra, we can easily find x1 and x2. So let's do that quickly here. So from deriving from the second equation, we get that x1 is equal to 14 meters minus x2. We will substitute the value of x1 into our first equation, giving us 15 newtons times 14 meters minus x2 is equal to 20 newtons times x2. We'll multiply inside our bracket 50 times 14 is 700 Newton meters. 50 times x2 is minus 50 newtons x2, which is equal to 20 newtons times x2. We will move this term to the other side of our equation, giving us 700 Newton meters is equal to 20 Newton times x2 plus 50 newtons times x2. Notice that when we move the 50 Newton x2 to the other side of the equation, the sign changed from negative to positive. Now, moving on forward, 700 Newton meters is equal to, we will take x2 as factor 20 newtons plus 50 newton. Now 700 Newton meters is equal to x2 times 70 newtons. Divide both sides by 70 newtons now. This cancels with this. Newton cancels with Newton. 0 cancels with 0. And 7 divided by 7 is 1. 70 divided by 7 is 10. So what we're left here is with 10 meters. 10 meters is equal to x2. x2 is 10 meters, meaning the distance from the center of mass to our second object is 10 meters. The remaining distance would be 4 meters. So here, our center of mass is now found. Have a good day, guys.